Dear all, my name is Jianhuan Tang. I'm with the Center for Millimeter Wave Smart Radar System and Technology in National Yangming Jiaotong University. Today, it is my pleasure to present our major achievement in the area of millimeter wave large tile-based phase antenna array and the wideband RFIC. Paradigm shifting of radar applications include shifting from fixed to mobile and from military to consumer. All these are due to faster growing technologies in many areas, including semiconductor, SoC, communications, AI, and fast computations. However, more technology advancement are required, such as the first one to reduce size, power, or cost of radar system. The second one is to increase the capabilities of resolution and algorithm. In 2018, DARPA proposed a project called Millimeter Wave Digital Array, MIDAS. In the proposal, DARPA seeks innovative proposals for the development of elemental level digital beamforming array technology. The primary goal is shooting for a tile-based subarray. The size of the subarray can up to 10,000 array elements in the frequency range from 18 to 50 gigahertz band. Two core technologies are required. The first one is digital RF silicon tile at 18 to 50 gigahertz. The second one is to develop wideband antenna and the transceiver components. To meet MIDAS requirements, we had successfully developed an ultra-thin low-loss and a wideband tile-based phase array and the full K-band RFICs. Innovative achievements are shown in the following three categories. Wideband antenna, and the second one is integration of K-band tile-based 4x4 antenna array and 2x2 RFIC. The third one is a wideband RFIC. Here, a novel 3D broadband double curve air cavity patch antenna has been proposed. The novel double cavity can enhance antenna bandwidth effectively, which solves cavity antenna drawbacks of narrow bandwidth. According to the benchmark table shown in here, it is found that the proposed antenna has the leading advantage in bandwidth enhancement and the size reduction. A novel low-profile, wideband, and the dual-polarized ME dipole antenna is also proposed. The figure shows side and perspective views of the proposed antenna. In designing the antenna, there are two technical breakthroughs. The first one is applying the Mindering via method to achieve the ultra-thin goal, and the second one is to use the shorting pin method to generate additional TM10 mode that compensates the narrow frequency response using the Mindering via method. The simulation results shown in the figure demonstrates that the antenna element covers the full K-band. These photos show the pictures of 1x4 ME dipole antenna array. The major result shows that the proposed antenna array operates from 26 to 42 gigahertz that covers the whole K-band. The peak gain of the array antenna could up to 12 dBi. According to the benchmark table shown here, it is found that the proposed antenna shows many leading advantages, including bandwidth, 3 dB, GBW, and the thickness. Here, the 3D physical layout footprint demonstrates that we had completed the integration of K-band tile-based 4x4 antenna array and the 2x2 RFIC. The beam switching function of 4x4 antenna array has been successfully validated with a near-field measurement method. The video shows that the result of the measuring 3D beam is switching, which prove our 4x4 antenna array work functionally perfect. Now, finish my talk. Now we will introduce our next speaker, Professor Cai-Zhuo Min, to present next our research result. Thank you.
We propose a frequency reconfigurable phase shifter with new switch substrate shield inductor technique. It is the first switchable frequency switching type phase shifter in 2 bands. From the comparison table to the published state-of-the-art phase shifter, we can find this phase shifter can achieve leading performance in both 28 GHz and 39 GHz. To achieve the phase shifter switching frequency function, we apply switchable inductors in each phase shifter unit. In each switchable inductors, we apply substrate shield inductors below the inductors. These substrate shield inductors can induce the current. Then the current can change the magnetic flux density. By switching the induced current, when we can switch the equivalence inductance of the inductors, then the frequency switching function can be achieved. Next, we propose a novel differential phase shifter using high-pass, low-pass phase shifter technique. This phase shifter has wide band response from 35 to 43 GHz. It is a zero DC switching type phase shifter. It has low insertion loss and the lowest amplitude error and the lowest phase error. From the comparison table of the state-of-the-art phase shifter, it has the leading performance of in the lows and the errors. In conventional, the switching type phase shifter switch the phase shifter between the through state and the filter state. The filter could be low-pass filter or high-pass filter. However, because the difference of the frequency response between the through state and the filter state is different, so the operation frequency is limited. In our new design, we switch the state from the high-pass filter and the low-pass filter. In this case, the error can be suppressed even in large phase shifter unit, and we can achieve lowest amplitude error and the phase error response in wide bandwidth. We also propose the production line solution for millimeter wave IC. It is a successful proof of concept of highly integration frequency conversion module on the load board. The frequency conversion module including mixer, LO chains, and couplers. It can significantly reduce the cost and the size of the automated testing equipment on the production line. Now, we currently work through an industry academy project with the world-leading packaging and testing company and the Ministry of Science and Technology with a funding size over $4 million. This is the summary. Our project has the academic contribution of 4 published IEEE journal papers. The industrial applicability of technique, this project has successfully developed a small size ultra-thin and low loss tile-based K-band 4x4 phase array antenna. We currently work with E3 to jointly develop a tile-based antenna array for B5G, 6G satellite payload through an industry academy joint project with a funding size of $800,000. The proposed 3D double curve air cavity has been proven to increase 70% antenna bandwidth without increasing the size. A manufacturing process pattern was typed. The proposed low-cost, highly integration millimeter wave module technique significantly reduced the bottleneck from the cost of millimeter wave automatic testing equipment in production line. We currently work through an industrial academy project with a funding size over $4 million. Thank you.